Hi, I'm Rachel Teater, a third-year PhD student in the Center for Rehabilitation Engineering and Assistive Technology. Today, I am presenting my work on evaluating functional deficits in transtibial prosthesis users during common daily movements. There are currently over 1.6 million lower limb amputees in the United States, and this number is expected to grow as we are experiencing an increase in amputation surgeries each year. The vast majority of these individuals wear a passive ankle-foot prosthesis made of carbon fiber or another composite material. Typically, these passive devices have a stiff ankle joint and a rigid foot plate that do not allow the device to provide any amount of ankle or toe flexion. Additionally, the majority of existing design and evaluation research with prosthetic devices has focused on characterizing their performance during walking and other locomotion tasks. But there are a lot of movements and activities we do in our everyday lives involving our lower limbs that aren't strictly locomotion. These are activities such as standing up from a chair, picking an item up off the ground, or squatting down to unload laundry out of the dryer that are necessary for everyday living and for recreation. Unfortunately, we know that prosthetic device users struggle with these types of tasks, creating mobility challenges that can impair their quality of life and affect their independence. Research surveys of prosthetic device users has shown that 11% are unable to stand up from chairs, 25% are unable to pick up an item off the floor, 41% are unable to get up off the floor themselves, and 40% do not have independent household mobility. We also have seen these challenges when directly working with prosthetic device users in our lab. This is a prosthetic device user we frequently work with who expressed how uncomfortable he feels and unstable lunging forward with his prosthetic device as his front leg, and you can see that here. This often limits his motion, like reaching for an object in front of him or doing lunging exercises at the gym. This is another prosthetic device user we frequently work with, and in this video, he's expressing to me the frustration he has with not being able to sit on the ground comfortably or work on his knees. He's a contractor, so he frequently wants to be working on the ground to do tile work or just to be on the ground to play with his grandchildren. But because of the rigidity of his device, here he's pointing out the hamstring tightness and other challenges he feels while sitting on the ground or trying to be there for a long period of time. Instead, his only alternative is to completely remove his leg to spend time on the ground. And then he also, here you can see, needs to use it as a crutch to stand up. This has led to our overarching research question of, can we help prosthetic device users overcome deficits by improving prosthetic device design? And ultimately, to answer this question, we first need to characterize their baseline abilities in their passive prosthetic devices. This led to our two research objectives for this study. First, we want to characterize the performance of lower limb prosthesis users during essential everyday movements while wearing their passive ankle-foot device. This will serve as a baseline and help us understand the strategies and deficits that exist when they complete these functional movements. To address this first objective, we developed a protocol that users go through that involves a series of everyday tasks. We chose these tasks because they represent movements that we know are challenging for prosthetic device users from the literature, from directly speaking to them, and from talking to physicians and prosthetists. During all of these tasks, we observed any functional deficits that the users experienced and collected the force under each foot using our in-ground force plates, as well as the motion of their lower limbs in our motion analysis lab. Now I'm going to present some preliminary data from one participant for a couple of tasks from this first objective. We had users perform several sit-to-stand tasks, as this is known to be a demanding task for many prosthetic device users and one that is essential for independent living. And what we saw is that the participant consistently put considerably more force through his intact limb than his prosthetic limb throughout this task and across variations of this task. We also evaluated the users during squatting. We chose this task because some of the prosthetic device users we work with mentioned that they did not even feel comfortable attempting this task because it feels so unstable. When this user attempted this task, we again saw a similar trend as the sit-to-stand task, where he had considerably more force going through his sound limb versus his prosthetic limb. The third task I'll show you is lifting. We had them all do several representative lifting tasks, and the trend continued. Here you can see the participant's intact limb often experienced twice as much force as his prosthetic limb. And this reoccurring pattern across tasks and across variations was very concerning because this asymmetric strategy for completing these tasks could lead to continual overloading of their intact limb. And this continual overloading day after day could contribute to an increased risk of overuse injuries and degenerative joint disorders in this intact limb. For instance, we know specifically that prosthetic device users are 17 times more likely to develop knee osteoarthritis in their sound limb than age-matched healthy controls. Potential prosthetic solutions that could move these two force lines closer together and promote a more symmetric strategy that offloads the intact limb potentially could decrease the amount of wear and tear experienced by that limb and reduce the risk of overuse injuries for users. So to go ahead and start testing prosthetic device modifications that could potentially accomplish this, we decided to use a powered prosthetic device. This allows us to systematically evaluate multiple design modifications and see if they benefit users while we have them complete some of these same activities of daily living. When thinking about what design modifications potentially could help users for these tasks, we thought about the tasks themselves. Squatting down, sit to stand, lunging forward, these tasks all generally involve ankle or toe flexion in healthy individuals, and these are degrees of freedom that are not included in most passive prosthetic feet. The lack of ankle and toe joint mobility may be contributing to the task performance deficits that prosthetic device users experience, and potentially design modifications that include flexion at these joints could improve the comfort, safety, and ability of prosthetic device users to complete these tasks. So that's where our research currently going. We are currently collecting data using the Vanderbilt Powered Ankle. This is a powered robotic device developed in Dr. Michael Goldfarb's lab here at Vanderbilt. We're able to program the ankle joint in this device to behave as a soft spring, so the user can have more flexion at the ankle joint, or we can program it to behave as a rigid spring and emulate more what their current passive device acts like. Additionally, we've modified the foot plate to include a passive flexible toe joint, so we also can evaluate if this helps performance during certain tasks. So users will come into our lab and complete these same tasks, the lunging, the squatting, the sit to stand, and we will see which design modifications helps improve their ability and potentially the force asymmetry that they're currently experiencing. Overall, main takeaways is that this work is establishing that the mobility challenges that prosthetic device users face during daily tasks may be due to the lack of ankle and foot flexion in passive prostheses. And then additionally, we're evaluating if adding prosthetic ankle and/or toe range of motion could potentially improve the comfort, safety, and ability of prosthetic device users to complete these tasks. I want to thank my mentors and the amazing team of researchers I work with, as well as my funding sources. And I would love to answer any and all questions or just chat about my work, so feel free to reach out to me.